you some more pictures that show you, again, this idea of the rich complication of nature. But I want you to think, as I show these pictures, about what you get taught in your physics courses. Because in some sense, what you get taught in your physics course must be very misleading. You get taught equations. You can be put on a few blackboards, or in fact, a small piece of a blackboard. And you get taught that things are basically fundamentally simple. Maybe like this. This is an Escher drawing, so that it's not quite as simple as all that. But here's a drawing of space as essentially repetitive, one thing after the other, just a simple repetition again and again of a basic object. But as we look at ourselves and our spouses and the weather and other things, we don't quite see this level of simplicity. Here is a baby lobster, in contrast. Now, a baby lobster has zillions of different parts. Each part has its own function. Each one is different. Each one is doing its thing. This living being was produced by exactly the same laws of physics that produces the relatively simple motion of the Earth around the Sun. Now, I'm not going to be able to talk about the full complexity that occurs in biological systems in life today. I'm going to be talking to some extent about a lower level of complexity in which you get objects repeated but somewhat different, somewhat changed either in size or in shape. So this is another Escher drawing which illustrates what I want to talk about. Here is this same object. Friendly fellow who we might want to give some name, like Oscar to, and here's Oscar written again and again and again and again. Each time turned around a little bit, each time a little bit different. In fact, this kind of simplicity or complexity, it's intermediate, can be seen in the world. This is a picture of a blackwood fern, familiar from any trip to the woods in the springtime. However, this fern has never seen the woods. This fern was produced on the computers of a bunch of people at Georgia Tech. What they said was, let's produce an object which contains within it a small copy of the same object, and then a smaller copy of the object, and a smaller copy again. So this whole fern is repeated in this one branch, and this branch here, or every branch, repeats the fern again and again and again. This is a kind of complexity which appears at an intermediate scale. In fact, mathematicians have thought some about this kind of complexity. Not quite as much as us or the lobster, but not quite as simple as the sterile space that we see in our mind's eye when we think about Maxwell's equations. Here's an object, which is a triangle. And now I'm going to tell you a rule for making something interesting out of it. We take each one of these gray triangles and fill those gray triangles with this object again. Here's the object. Now, with this triangle replaced by this whole thing. And now we take this gray triangle and put one of these in there, and here, and there, and there, and there, and there, and there, until we get this object. And then we do that again and again and again until we make one of these objects of intermediate complexity. And here's a drawing of one of them, actually made here at the University of Minnesota, or studied here at the University of Minnesota. A tiny object was made in a facility for capturing photographic images. Here is the real thing, kindly lent to me by Professor Goldman. Oh, he's going to be so angry with me. As the by producing an artificial material, and that artificial material having the complexity at hand. And here be the real object of that kind, and then people study, for example, the electrical resistance between 2 points in that network. So there's the real world of complexity to some extent. Here is one of my friendly, complicated creatures. There's a fractal that is repeated behavior here, and a face which looks like no other face in the world. Here, this is complexity. I would like to start to ask interesting questions about complexity. I asked one. My first question that I asked was, how could it be that the simple laws of physics could produce complicated objects? Then I want to ask another question, which is related perhaps to the swirls of water that you saw. When you pour water out of a vase, it swirls around in a pattern which is complicated, hard to predict. How could it be that the laws of physics, which are strictly predictive in character, can lead to the complicated and hard to predict patterns that you saw? But perhaps I shouldn't tell you about the complicated and hard to predict patterns in the flow of water. You can think about other objects that are part of the physical universe. You and me, we're both parts of the physical universe. Try to predict our behavior. We are hard to predict. And the question is, how can we, big parts of the world, be so hard to predict if the laws of science are fundamentally predictive in character? Now, I have a whole bunch of references here, which has some of the same topics that I am going to be covering or have covered. James Blick wrote a beautiful book, now in paperback, called Chaos Making the New Science. It's correct on the science and lots of fun on the people involved. Milton Van Dyke had published in his own basement. This is not the Cambridge University Press. This is his basement. He published in his own basement a beautiful book called An Album of Fluid Motion, where for $10 or $20 you can see great pictures of fluid in motion. I also showed you one picture from this book, The Beauty of Fractals, showing you some of how complicated things can be absolutely gorgeous. The fractal of this talk done for the Encyclopedia Britannica. How fractals, those ideas got introduced into science, is described in Benoit Mandelbrot's book, and these are other references, the virtues of which modesty forbids me to tell you about. Now, what I would really like to be able to do is take one of those hydrodynamic examples, maybe the jet of water coming up, and explain to you how complexity arose, what that thing is all about. I just love to do that, but we do not fully have the knowledge to do that. So instead, I'm going to choose a much simpler example drawn from population biology. I'm going to describe a simple mathematical model. And by the time we're done, I hope that all of you will agree that that simple mathematical model shows chaos, shows complexity and unpredictability, and that we can understand something from it. The model is very simple. I want you to imagine an island. Every year on that island, we have a bunch of insects who lay eggs. The eggs hatch. The insects live for a month or so. They lay eggs again. The insects die off over the wintertime, and the process goes on again and again. So we have an annual resurgence of the insect population, and what you end up with in describing the insects is a list. The list is the population after the first year, at the start, after the first year, after the second year, the third year, the fourth so forth. Now, some things seem very regular. Other things seem very irregular. For example, if Minnesota is like other places, the populations of mosquitoes year by year are very hard to predict. Some years there are lots, some years there are a little bit. And what we want to do is talk about how the population of insects in one year produces the population in the next year. In this very simple model in which we have an isolated island and only one kind of life form, we can have a simple mathematical model. Model means simplification from which we can learn. That model is a statement of the number of insects next year depends upon the number of this year. Mathematically, let's say the number next year is a function of the number of this year. T stands for the year that we're looking at. The questions we want to ask are what kinds of patterns are possible in this list. Can the list settle down to some kind of orderly behavior? Can it be irregular and chaotic looking? So now I have to tell you a little bit about mathematical models. Now, I'm going to assume that I have a very wide variety of backgrounds in this audience, but I will assume that you remember a little bit from your high school algebra. Maybe I've got to the thing that everybody has forgotten, namely their high school algebra, but okay, at least it's uniform. The first model I'm going to do is compound interest, which we can all remember how we suffered. In year 0, let's imagine we have $1,000, and here we are, times t equals 0. Imagine that the bank was giving us 8% interest, so that after a year, we would have 8% more than $1,000, or 1,000 times $1.08, or $1,080. The next year, you get the same amount of increase. You multiply the same factor. You get the same multiplication factor. So you take this 1080 and multiply it by 1.08 and get this amount, which is 1,000 times 1.08 times 1.08. And you continue on step by step on in the same fashion, so that year by year the assets go up in an apparently predictable fashion. Now, as mathematical models are, things have been left out. No inflation, no taxes, all of the things that make life so interesting have been left out. But the consequence of the model is if you started out with $1,000, year by year, the amount of money you would have would go up, so that after 25 years, you'd have $6,400. Now, you can talk about insects in exactly the same way. You can apply precisely the same model to insect behavior, and what you say is that NT is the number of insects in year T. Use N as a general symbol for the number of insects. You say R is the population increase factor. That is, in year 0, I might start out with N sub naught insects. In year 1, I might then have, according to the notion that there's an increase by a factor R in each year, I might have N1, which is R times N naught insects. N naught might be 1,000 insects. The population increase factor R might be 1.08, and that might be 1,080 insects. In general, we know how to handle this kind of law. In the next year, we would have R times the number of insects in year 1, which is R times the number in year 0, which is R squared times the number in year 0. In the next year, you would have R cubed times the number of year 0. In the year T, you would have R raised to the power T times the number in year 0. Now, at this point, if this is the first time this kind of thing has been done, a mathematical physicist like myself gets all enthusiastic, muttering things to himself like, or herself like, I've got an exact solution of this problem. That's a wonderful thing to have, because by just looking at the formula, you can see something about the behavior. For example, if the population increase factor R is bigger than 1, then year by year the population goes up until the population increases but without bound. If R is less than 1, the population decreases year by year until the population goes towards 0. There are indeed two different behaviors, but this increase without bound is somewhat unrealistic, and we want to make a better model. Okay, here we go from trivia to the more interesting stuff, because I'm now going to construct a mathematical model, in principle very much like the compound interest models that we all saw in high school, but now with interesting properties. That's the name of the model. Let's again think about insects. Our old model, we had the number next year is R times the number in the year before. R, number next year is R times the number in the preceding year. However, let's make some assumptions about overcrowding, reducing the viability of insects. Mathematically, that is a term in the population next year which depends on the number of interactions one can have between insects in this year. That number of interactions is the number of insects squared, or more technically, n times n minus 1 over 2, but who cares about more technically? Let's call it n squared. Okay. That number of interactions then reduces, with the minus sign, of course, if b is a positive constant. That reduces the number of insects we will get in the next year. A number like R or B are called parameters in technical discussions of models like this. What that means is that they are properties of the system that does not change in time. These represent, for example, properties of the island. R might be how much vegetation naturally grows on the island. B might be a limitation produced by lack of nesting space. B is a parameter that represents the bad effects of overcrowding on the population. You can choose to think of that as you will. For example, it might be competition for food or nesting space. In my more kind moments, I think it's the insects aren't reproducing too well because when it gets too crowded, the fact that they're shy gets in the way. Okay, but in any case, whatever I think, I want to do some fussing to get the model in reducible form, and so I'll define a new variable that I call xt. A variable is something that changes in time. Parameter is something that remains fixed. I'll define a new variable called xt in this manner. That is the ratio of the number of insects that exist on the island to the maximum number that the island can hold. And when I do that, the model turns out to have this form, which I can then factorize and write this way. The number next year is a growth factor times the number this year times another factor, 1 minus xt, which represents the bad effects of overcrowding. Now, we've done hard stuff. Let's see if we can get some consequences from it. First consequence. I want to look at the case of R between 0 and 1. This is a situation in which the natural growth will not keep the island going with insects. The population will drop in any case. The extra factor of 1 minus x, the overcrowding, will just make the drop-off occur more rapidly. The population, it says here, will naturally go down each year. Now, I want to emphasize to you what a simple mechanical process using a model like this is. I often do that by bringing a hand calculator and punching in the numbers and saying what you have to do if you're given a value of R and the value of the population. To get the population in the next year, the population ratio, you put R, which is 0.5, R is 0.8, you put 0.8 there, times 0.5, times 1 minus 0.5, or 0.8, function of years. Sometimes I'll use T to represent the year, sometimes J. Here's J. This is the first J equals 0, then the population goes down and down and down until it becomes indistinguishable from 0. And now I want to collect up my results a little bit, and in collecting up the results, what I want to do is draw a picture of, as a function of R that describes the population increase rate in the island, I want to describe what happens to X in the long run. And here, R between 0 and 1, X turns out to be simply 0. The population goes down to 0. Now, everybody should be up to speed on what a model is and why models might represent to some extent what's interesting. What I want to do now is get into gear and start talking about more interesting situations. When R is between 1 and 3, I don't have any chaos. I still don't have any chaos. There's no chaos there. But something more interesting happens. If I started out with a small population, if the natural growth factor is between 1 and 3, then the small population will go up and up and up in the first bunch of years until this factor of overcrowding starts to limit the growth, and eventually we come to a situation in which the growth levels out and we reach a fixed population. Let me show it to you here. I built the wrong picture. I started out with a low population. The story would go just about the same way. We started out with a population in year -1, which is about here. I'd have the population go up and then up and up and up until it leveled out and became flat. Here for R is equal to 2. In fact, without doing any very hard algebra, we can see what that flat population would be. Here's our box. What we're saying is that after a long time, the population reaches some fixed value. Let's call that fixed value X with a star above it. And then we say in year T, the population is X star, and in year T plus 1, it is equally well X star. So the equation for the population is X star here, X star there. X star is R times X star times 1 minus X star. Aha! Something else we remember from our high school algebra, or have forgotten from our high school algebra, quadratic equations. But fortunately, this one is real easy to solve. There are two solutions. One I'm going to ignore for a moment. X star equals 0. That's no insects. I'll factor that X star equals 0 out of the equation. And then I get, when I factor, I say X star is different from 0, so I take the common factors of X star out of the equation. I'm left with the equation 1 is equal to R times 1 minus X star, or X star is 1 minus 1 over R. This population, in this range, once again, we have a situation in which we reach a steady, non-chaotic population value, and that population value is given by the formula 1 minus 1 over R, which I'll plot here for R between 1 and 3. Oh, there is another solution, but we as experienced people know all about the other solutions. There's a solution X star equals 0. That's the solution you have when you don't have any rabbits at all in your house. Bring 2 rabbits in your house, and then you know that you're going to soon have a large number of rabbits. The X star equals 0 we call unstable. It is unstable to have only a few rabbits because they breed too rapidly, and similarly our insects do that. If we started out with a small number of insects, pretty soon we would have a large number. Now, I have here a picture which is just identical to the one I drew on the blackboard. It's now just drawn on the piece of plastic. going to go on to the next step. I'm going to jump from r equals 3 to r equals 4. We'll come back and go back over that territory between 3 and 4 later. But I want you to see that for r equals 4, we indeed have chaos. So let me show it to you. Here is the population in year T, or rather population ratio, the number of insects on the island divided by the number of the island in whole. I'm doing a case in which r equals 4. I happen to have chosen 0.77 as my starting point as year T equals 0. The population goes up and down with a starting point in a way which doesn't look very easy to predict. In fact, if I show you 100 years of insect history, and the blue dots are for the people at the very back of the room who can't see there are 10 blue dots and there are 100 black dots. The blue dots or the black dots or whatever produce a pattern, year-by-year behavior, which is very hard to predict or to understand directly. But remember, there is nothing more in this complicated and chaotic appearing picture than our basic equation. And our basic equation is, I repeat,